Hello, this is a talk on profit inequalities with cancellation costs. I'm Jan, and this is a paper with my great co-authors, Farbod Ekbatani, Radniazadeh, and Pranav Nuti. All right, so this talk is about profit inequalities. So let's start with the classical problem. We are given a sequence of distributions, D1, D2, so on, and values are sampled one by one from these distributions, and we observe the values x1, x2, and so on, one by one. And at some point, we have to say we accept the current variable. We don't know what the future variables are going to be, and we commit to selecting the current one. This is a classical stopping rule problem. The goal is to maximize the expectation of the variable that we select, and we want to compare to what the profit would have selected, which is the maximum value among the n random variables. So we want to compare to the expectation of that. And this is a very classical problem, which was solved in the 70s. And the result is known as the profit inequality, which says that there is a stopping rule such that you select a variable whose expected value is at least 1/2 of the expectation of the actual maximum. So that's a beautiful result, which has several different proofs. Maybe the two simplest ones are that either you wait until you see a variable which is at least the median of the distribution of the maximum, or you can also wait until you see a variable which is at least 1/2 of the expectation of the maximum. Either of these two rules will give you a stopping rule that achieves at least 1/2 of the expectation of the maximum. Now, since this classic result, many variations have been considered. There's a vast body of literature that I don't really have time to survey here, but let me mention a few works somewhat relevant to what I'm going to talk about. So the extensions and variations on the profit inequality went in several different directions. One is in terms of the set of elements that we are allowed to select. Instead of being just one element, we can aim to select multiple elements subject to a certain constraint. Different types of constraints have been considered. Maybe the most elegant result here is for a matroid constraint, where you can still obtain this optimal factor of 1/2 for any matroid constraint. That's a beautiful result by Kleinberg and Weinberg. Other extensions have been along the lines of relaxing the assumptions on the distributions, or making them more stringent, like assuming that all the distributions are identical, or having less information than actually knowing the distributions. Maybe we only have one sample from each distribution, and so on. So there's a huge body of literature here. And the third direction I want to mention, which is the most relevant one to our work, is variants of the problem where we don't necessarily have to commit to a solution irrevocably, but we can still change our decisions later at a certain cost. Now, you can model that in different ways, and I listed a sequence of different works here, which have done that in different ways. But what we do in this paper is based on a model introduced by Babayev, Hartline, and Kleinberg 15 years ago, which is known as the buyback model. So this is a very clean model where we say, if we are currently holding a variable xi, we can still discard it and select some other variable later, but we will pay a buyback cost, which is a certain fixed factor f times the value of the variable that we are discarding. Now, we are going to be talking about the very basic version of this problem, where we only aim to select one element. So we are back to the classical setting, selecting one element, but we can make multiple decisions where we discard a variable that we selected before, and we replace it by a new variable. Let me show you an example of that. So here's a sequence of variables. Maybe the first one ends up being 10. So I say that's pretty good. I'll accept 10. The next one is 1. That doesn't make sense to accept 1, so we just skip that. The third one ends up being 100. So I say, well, that's very good. I'm willing to discard the first one, even though I have to pay some penalty, and I will accept 100. So my payoff in this case will be 100 minus the buyback cost, which is 10 times the buyback factor F. Now, of course, the decision between buying back or not depends on what the factor F is. So the aim of this work will be to characterize what can be done given a certain value of the buyback factor F. All right, so there was a sequence of papers about 15 years ago which considered this problem in the worst case, which means that the sequence of values x1 through xn is given by an adversary. We don't know anything about these values in advance. They're not even randomly permuted, anything like that. They're just coming in an adversarial order. So without the option of buyback, there's nothing you can do. But with buyback, you can actually achieve some nice results. And quite remarkably, these papers identified the exact optimal curve as a function of f, which tells you what is the optimal factor that you can achieve in this setting. So the curves look like this. There are two curves. The blue one is for deterministic algorithms, and the purple one is for randomized algorithms. It's some pretty non-trivial answer in both cases. But the curve looks qualitatively like what you would expect. As f tends to 0, it approaches 1, because with 0 buyback cost, you can just find the actual optimum. And as f tends to infinity, the factor tends to 0. So that's pretty intuitive, but proving these optimal curves was not easy. Now, in those papers, they also mentioned the Bayesian setting, where you have some prior information about the distributions that these values are coming from, but they didn't really explore that direction. So that's actually the setting that we explore in this paper. It's a very natural problem, which combines features of the profit inequality and the buyback setting. So we are given distributions d1 through dn and a buyback factor f. And you want to design a policy which is allowed to switch from one variable to the next one at this buyback cost. And you aim to maximize the expected reward at the end, which is the value of what you have at the end minus the total buyback cost that you have paid in the process. All right, so for sure, we can get at least 1/2 because we can get that even without buyback. We can also get what the purple curve is telling us because we allow randomization. But some interesting questions remain. For example, for f equal to 1, can we actually do better than 1/2 or not? What about f equal to 2? Can we get better than 1/2 for any fixed value of f? So that's the kind of question that we were exploring in this work. And the ultimate question here is to identify the optimal curve. All right, so here's what we can prove in this paper. There are two main results. One is that for f greater or equal to 1, we identify the exact optimal factor, which turns out to be 1 plus f over 1 plus 2f. So a relatively simple formula. That's the optimal curve for f being at least equal to 1. But in fact, we know that this is not the answer for f less than 1. For f approaching 0, we identified the behavior of the curve. It's roughly 1 minus some constant times f log 1 over f. So that's the way it behaves close to 0. And it's instructive to compare that with the previous result in the worst case setting, which is some more complicated formula, but it behaves like 1 minus square root f close to 0. So in the Bayesian setting, you see that the curve approaches 1 much faster, which shows the benefit of the knowledge of these distributions. Now, we actually have ongoing work, which I will not talk about in this talk, but we know more information now about the curve than what is presented in the paper. There's an emerging picture which is more complicated, and the curve has a sequence of intervals where there are discontinuities in the second derivative of the function. I'll get to this briefly at the end of the talk. So, okay, these are the main results. So how do we do these things? Let's start with a very simple example, which is the motivating example for this work. A classical example is showing that you cannot do better than 1/2. For profit inequality can be modified in a natural way to give the following. You have two variables. The first one is just 1. The second one is 1 plus f with probability 1 over 1 plus f. So it's set up in a way that no matter what you do, you will never get value more than 1 with an algorithm. But the expected optimum turns out to be 1 plus 2f over 1 plus f. So that's the gap. And this is the starting point of this project. Is this actually the answer to this problem or not? Okay. But when you dig in a little bit deeper, you will see that with multiple variables, you can get some more interesting examples. With 3 variables, you can set up 3 variables in a way that gives some hardness factor, which is slightly worse when f is less than 1. So you can see that in the graph here, in the interval 0, 1, you actually shave off a little bit more by an example with 3 variables. And you get some function involving square root, which looks like this. Now, you might remember we had some function like that in the worst case, but it's not the same function. It's different, and it's just a coincidence. There are some square roots, but as you go to multiple variables more than 3, it gets more and more complicated. So it's not clear what the answer should be. Nevertheless, we were able to prove something. With multiple variables, you can construct an example where the number of variables is roughly log 1 over f, and the hardness factor behaves like what I said, 1 minus constant f log 1 over f. So that's the behavior that we conjecture to be the right one, close to 0, and indeed that's what we proved. Now, how do we prove positive results for this problem? We have 2 algorithms which work well in the 2 different regimes that I mentioned. When f is small, we are using a very natural threshold-based strategy, which I will describe next. And this gives the result that I mentioned, 1 minus f log 1 over f. It also works relatively well for large f. It gives some improvement over 1/2, but it's not the optimal answer for sure. To obtain the optimal answer, we use a different strategy, which is based on linear programming, which captures the optimal policy. And then the question is, how do you analyze this linear programming? So I will actually talk more about this. This is the approach that we believe should give the optimal answer for all values of f. So the current picture looks like this. We have 2 algorithms where the region between them we don't understand that well. And then we have hardness curves in different regions given by examples with different numbers of variables. And for f greater or equal to 1, these curves coincide, so we know the answer exactly. All right. So what is the threshold-based algorithm? That's a very natural approach that you would probably come up with if you want to solve this problem. In practice, this is something like what I would do first. So you set some threshold, t. Now we actually pick something like median of x max, so very natural. And you wait. First, you wait until you see something above the threshold. You accept the first variable, which you see above t. And then after that, you buy back, you switch to another variable if that brings you any benefit. So if the new variable is more than 1 plus f times the variable that you are currently holding, then it's worth swapping, and that's what you will do. You could say that maybe this strategy is swapping too easily because you swap even if the benefit is very tiny. But in any case, this is what we analyze, and it gives some reasonable result. As I mentioned, it gives asymptotically the right result for f approaching 0. I will skip the analysis because we don't have time for it. It can be viewed as an extension of the classical profit inequality, but quite a bit more complicated with some interesting tricks like Poissonization and the FKG inequality. But I'll just skip that here. You can look it up in the paper. I'll talk a little bit more about the LP approach, which we believe should give the right answer in all settings. Now, how do we set up the LP? So first, let's assume for simplicity that we have what we call monotonic instance, where we have a sequence of Bernoulli variables. Each of them attains either 0 or some positive value, and the positive values are also monotonically increasing. We actually prove that this is the worst case that we can reduce to this instance. So let's just assume that the instance looks like this. In particular, the hard instance on two variables is an example of that. There's just two variables. Both of them are Bernoulli, and the second variable is bigger than the first one. So in a setting like this, you can actually aim to design a strategy which is sort of oblivious to the values, which is nice, in the sense that we only set up certain probabilities of switching from variable xs to a variable xt, and maybe we can set up those probabilities in a way that we extract from each variable the value that we need to extract. What I mean by that is that the total benefit that we get from that variable minus the total buyback cost that we pay for discarding that variable is comparable to what the optimum receives from that variable. So when you write that down as an LP, you get this kind of linear program. A little bit hairy. Let's not dwell on it too much, but I want to say a few remarks. So theta is what we maximize. That's the factor that we aim to achieve at the end. Now we have these variables x, I, t, and so on. So these are the buyback variables, the probabilities of switching from a certain variable to another variable. The variables x0, t are the probabilities of initially selecting variable xt. Okay. Then we have these parameters qt. Now these are not variables in the LP. The program is nonlinear. These variables qt, these are the probabilities of the Bernoulli variables attaining a non-zero value. Okay, so for the purpose of this LP, we view them as fixed parameters. At the end of the day, we still have to deal with them somehow. We have to identify the worst case for these parameters qt, which is the difficulty of this problem. There's some inherent nonlinearity in the problem. But nevertheless, this LP captures what is sufficient to achieve a certain factor theta, right? It looks like maybe we've made our problem harder by requiring that we extract at least some fraction from each variable. But in fact, by LP duality, you can show that you are not losing anything by this step. This captures exactly what the optimal theta is. All right, so now it remains to solve this LP somehow and also deal with the fact that we don't really know what the worst case probabilities qt are. Now, a good point of view here is that this is really some kind of flow problem where the variables x, s, t are like flow variables, except it's a generalized flow where flow is not quite preserved, but there's some flow lost along each edge. And this loss is exactly related to the buyback cost f. In addition, we have these other constraints that I did not talk about, which we call online implementability, which are the constraints that capture the ability to actually implement this in an online fashion, in the sense that when you get to a certain variable, you still have enough probability left to select it or to buy back from a previous variable. I will not get into this in detail. Let me just say the following. The LP looks pretty difficult to just solve by hand. And the way we solve it is by simplifying the whole problem by just postulating that the solution might have a very simple structure. In the simplest possible case, it has a structure like this, that there are just two blocks where buyback only happens between the two blocks. So you could imagine that there's a breakpoint somewhere in the middle. Until that breakpoint, you never buy back. After the breakpoint, you might buy back. If you're holding a variable from the first block, you might switch to a variable in the second block, but you never switch within a block. Why would we do that? Well, because we want to mimic what is happening in the hard instance on two variables, and we want to achieve the same factor that that instance achieves. So somehow we want to believe that for a general instance, we can somehow match it up with the hard instance on two variables, and we can do something similar to that. That actually turns out to be true, but only for f greater or equal to 1. So the actual solution, uh, even in this two-block setting, uh, took a long time, many iterations of trial and error. Using the Maxwell-Minkowitz theorem, we got some intuition about how to do this, and eventually we identified a pretty simple form, which looks like this. So this depicts what is happening with the two blocks. The purple curve is the probability of the initial selection of a variable, and the two blue regions, they represent the buyback between the first block and the second block. And the blue arrow represents that we take a certain probability of having a variable in the first block, and we switch from that to a variable in the second block. And we want to transfer the mass from the first block to the second block in a very careful way that achieves exactly the correct density everywhere. Okay, so I'll just leave you with that. This solution works for f greater or equal to 1, and it leads to the result that we announced. In ongoing work, we actually have more information, which is not in the paper, and we believe that this will lead to a complete solution of the problem, but it gets more and more complicated as f tends to 0, the number of blocks grows, and the solution is described less explicitly. So stay tuned for more on this problem. Thank you.